Hello everyone, let's move on to our discussion on part 2 of module 4. Module 4 is basically dealing with the multiplexing techniques, and we already seen an overview of multiplexing, its relevance, everything, and the classification also. So here we move on to our discussion on a particular technique in detail. So this is an overview that we saw in last session also, that is a frequency division and the time division multiplexing. Frequency division, you can see this kind of a horizontal division, where in time division the time is being divided. Okay, here the bandwidth, that is a range of frequency, is being divided into different channels. Okay, so in this part we will see in detail how this frequency division multiplexing is working. So this is the idea. The total bandwidth is divided into different small sub bands like that. So if this the entire medium we call as carrier, each channel we can call it as a sub carrier, something like that, and each sub carrier is centered on a particular frequency, say f1. Centered on this frequency, this much range of frequency is being allotted to channel 1. Similarly, this like that, you can hear it is a division of 6 channels. You can think of more division also depending on the requirement, but there is no splitting of the time. So between a sender and device, the whole subcarrier is being allotted to a given communication without any disturbance. So that is the idea. Now this nearby frequency should not be means there should not be any overlapping between them, or some part of the information being spread to other one, or something be coming to this one. Such overlapping related issues should not be there. To ensure that, normally between two channel we will give some kind of a space. That means some very small set of frequency we will give as a gap between two channels, just to avoid that interleaving kind of issues. Okay, and that is what we call as a guard band, and that is not shown in the figure, but in general you can assume some small frequency band is being between these two channels. Okay, between every. So here we have a 6 channel. So how many guard bands are needed? 5, because 6 channels will be separated by 5 guard bands, right? So that is the idea. And let's see. Frequency division multiplexing is possible when the useful bandwidth of the transmission medium exceeds the required bandwidth of the signals to be transmitted. Okay, so we have a common medium. The total bandwidth of the common medium is more than what is needed by the individual devices. So we can divide that bandwidth of the common medium, and we can share among the individual devices. So common applications of FDM in AM and FM radio broadcasting and cable television are two situations where we are typically using this frequency division. So the radio itself, you may be familiar, right? Tuned to a particular frequency to get a particular channel. So that is the idea. Simply that is what is happening in frequency division multiplexing. Similarly, cable TV also, you are tuning to a particular frequency band to get a given channel. Okay, say you are giving a number and you are getting that channel. On the background, you are tuning to that particular frequency band. Okay, same thing. So that is something which we all are using every day, and the technique in detail we are seeing here. A number of signal can be carried simultaneously if each signal is modulated onto a different carrier frequency, and so individual signals are to be modulated to a different carrier frequency, like what is shown, like F1, F2. Okay, and the carrier frequency is sufficiently separated that the bandwidths of the signals do not significantly overlap. To ensure this, we are using that guard band. Okay, so this word guard bands. Now in the previous slide, figure A, the first part of the figure, we saw 6 signal sources are being fed to a multiplexer, which modulates each to a different frequency. Okay, and each modulated signal requires certain bandwidth centered on a carrier frequency, and that is what we call that frequency range of frequency centered on the carrier frequency given to a particular communication is what we call as a channel. To prevent interference between the channels are separated by guard bands. That is the unused portion of the total spectrum. So a very small frequency range that is not being used. Okay. Now, FDM is an analog multiplexing technique that combines analog signals together. So, typically, it is preferred for analog communication. Now, even though it is digital communication, we can convert using a modem to convert the individual digital information to analog, and we can apply FDM. Okay, so the composite signal transmitted across the medium is also analog. The individual input line should carry analog information to be multiplexed using FDM, and also the resulting signal is also analog. So it's a kind of analog to analog multiplexing. Note, however, that the input signal may be either digital or analog. So, in case of digital input, the input must be passed through a modem to be converted to analog. And those things, how this modem working and how that conversion is done, that we saw already in module 3. So, each input analog signal must then be modulated to move to a particular frequency band. So this is the diagram I taken from William Stalling's textbook that illustrates the overall process. So like what we seen, the individual information is coming like M1 of 2, M2 of 2, say n input lines are there, and subcarrier modulator. So this modulator is converting that information into analog signal, so that the output is analog. Okay, so if the input is digital to analog modulator you can use. If the input is analog to analog modulator you can use, provided the modulator is converting the input information into an output information that is being summed up to the common carrier. Okay, so all the individual signals that is being generated by the devices are now suitable to be combined into a common one using a summation unit here combining, and the combined the composite baseband modulating signal is what is denoted here. Means why it is baseband, because we didn't apply further modulation on it, just the combined signal, that's all. And now depending on the transmitter central carrier frequency, the common medium's carrier frequency, accordingly you can shift the combined. So here there is simply you are taking the individual signal and you are modulating it so that it is ensured to be analog with a different subcarrier frequency, and all these signals you are summing up to get a resultant combined signal. So we call it as a composite modulating signal and composite baseband signal, and means which can be further modulated so that it is suitable for the carrier frequency of the common medium. Okay, so that may be the medium may be providing a different spectrum. So the individual machines you are combining and the result you can modulate it to the spectrum that is suitable for the common medium. Okay, and the modulated signal is what is S of t, denoted by S of t. So if you are looking at the spectrum of the composite baseband modulating signal, the frequency domain representation of the combined signal, you can see that here you are taking the frequency, here we are taking the baseband signal as a function of frequency. Here it is a function of time, here it is a function of frequency, like that. Okay, the frequency domain representation. So each this corresponds to the bandwidth or the range of frequency provided for channel 1, channel 2, like that, and if there are n channels. Okay, and each one is centered on a particular frequency. So that about this diagram. Okay, so just a frequency domain representation. In x-axis we are taking the frequency, y-axis we are representing the signal as a function of frequency. Okay, and you know, if there are n channels, there will be n subcarriers centered on n different frequencies, and this is the range bandwidth of each one, of each channel. And now at the receiver side, what is happening, we are getting this combined signal which is being modulated to the carrier S of t, and that will be received, and that is being demodulated to get the original baseband signal, the composite baseband signal, and which is further means this is containing the information of all the n individual input lines, right? Accordingly it has to be splitted and given to the correct destination correctly. So what we are doing, the total signal, you know, each it is containing different channels is combined together, and each one is centered on a particular frequency. Now to get this part alone, what we can do, we can use a band pass filter centered on frequency. So what is done by a typical bandwidth filter is it will filter the total information, so that only the spectrum of information centered on the frequency f1 will be coming out as output of this particular filter. So this is a band pass filter that will pass the range of frequency centered on f1 as output. Okay, and that limit also you can fix like that. This band pass filters will be designed. Similarly, this will pass the spectrum of information centered on f2, and the last end band pass filter will be passing the from the common information. It will be selecting, kind of selection is done, or passing, or kind of filtering is done, the part of the signal that is centered on f1. And at the center side we done some kind of modulation to convert every information into analog, and at the receiver side the same demodulation can be done to get the original signal back, and that can be delivered to the individual devices at the receiver side. So this is the overall diagram. Now what you see in the diagram, I just explained here. So a general depiction of an FDM system is shown in the previous slide. Here the input signals Mi of t, so there are n input lines like that we assumed, are to be multiplexed onto same transmission medium, and each signal Mi of t is modulated using any modulation technique onto a particular carrier frequency, so that they can be summed up. Okay, because a multiple carrier are to be used, each is referred to as a subcarrier. The resulting analog modulated signal are summed to produce a composite baseband signal, and the composite signal can then be shifted as a whole to another carrier frequency that is being supported by the common media and the outgoing link. By an additional modulation step, it may be different from what is used in the first modulation. So here there is a kind of modulation that is used for the individual signals. Here the modulation is for the total combined signal. Okay, according to the carrier frequency of the outgoing link. So the frequency division multiplying signal S of t, the final output, has a total bandwidth B which is greater than the sum of the bandwidth of the individual signals. So the analog signal may be transmitted over a suitable medium. At the receiving end, the frequency division FDM signal is demodulated to receive the combined baseband signal MB of t, which is then passed through N. Just apply the reverse process. So you are getting that S of t, that is the output, right? And that is being demodulated to get the baseband composite baseband signal. Then using n band pass filters, each centered on Fi and having a bandwidth Bi. Then this MB of t as a whole is passed through n bandwidth pass filter. So each filter will be providing the portion that is being delivered to the receiver. In this way, the signal is again split into component parts, and each component is then modulated to recover the original signal. Okay, because at the center side we done a modulation to convert to analog form. Now you have to return back. If that modulation is not needed, if needed only you have to apply that modulation and demodulation, otherwise you can skip that phase. Okay, that about the overview. Now here this diagram I taken from that Forosin textbook. I felt it can explain the concept more pictorially than the complicated diagram that what we've seen so far. So it is something like this. So we have a baseband analog signal, say different signals, say 3 input, say from 3 input devices, 3 input lines, and the subcarrier 1, subcarrier 2, even this is the total carrier. So in William Stalin's textbook they are using the terminology subcarrier 1, subcarrier 2, like that, and with the different frequency. So this is the frequency, this is some other frequency. You can see that, right? You know what is frequency, right? And here you can definitely, it is different from the other two. So using a different frequency, first you are modulating so that it is suitable for this particular frequency. That is the first phase. So that now all these individuals, so this is the first level of modulation, and then they are summed up, and this is the resultant summation of all these three. And now this will further be modulated so that it is suitable for the outgoing that particular medium's bandwidth. Okay, it can shift to a different spectrum if needed. And at the receiver side we will get this and we will apply the reverse process. And to do that reverse process, here in this diagram, one additional modulation at this point is being explained in Stalin's textbook, and that is again optional. If needed, you can do that. So here it is not depicted. Suppose that demodulated signal is coming here, then using say n different band pass filter, we will convert it back to the individual representation, and using demodulator we will recover the original signal. So this is the idea. Okay, with this we will hope you got an overall idea about the frequency division multiplexing process. That is for your theoretical understanding. Now we will see some problems possibly you can expect from this area in the next part. Okay, and then we will move on to the remaining session of multiplexing. Okay, thank you.